Thank you very much for having me again, especially Tillman. It's always a pleasure to come back to visit, even in a very cold day. So here I'd really like to share some experience my group has for the last 5-10 years, and we try to distill into 3 different principles, and I'll tell you how we came up with these principles. Oops. So since I claim these are 3 principles for data science, I want to explain what's the definition for data science. So at Berkeley, actually, we have a group of us have been working very hard to have a data science initiative, including education and structure change. And the definition at Berkeley is the remerging of computational and statistical thinking in the context of domain problems. So common Venn diagram, computer science, math and stats, and domain knowledge, and you have machine learning. And it's meant to be in the middle, somehow always get projected into towards statistics. One important case to make the case why it's a re-emerging of statistical and computational thinking is this story of this statistician called Herman Horowitz, who worked for U.S. Census around 1890. In the U.S., every 10 years there's a population census. And 1890 was predicted that would take 13 years. So it would take too long before the next census data come in. So he was charged to speed up the computation. As a result, at the time, Edison just invented electricity and all that stuff. So using that for light. And he used that. I have a tabulating machine called Horowitz tabulating machine. And he had a company, and later was one of the 4 companies that merged into IBM. So this is an incident that statistical analysis or tabulation really drove computation device development. And Fisher, a modern founding father of statistics, was a scientist, right? He was never professor of statistics at Cambridge. He was also always a professor of genetics. And Pearson and Galton, including Fisher, were always very intrigued by Darwin's evolution theory, which tried to give some mathematical foundation for evolution theory. So that was the science bit. Data science, if you ask me, is really applied statistics. But I think data science is a better name, and I have no problem with it. And as I mentioned, machine learning is one of the most frontier areas, both in statistics and computer science. And machine learning put prediction at the center of its tenet. And of course, statistics, we always talked about prediction, but it was never like the most important thing. If you ask anybody about statistics, they're not going to talk about prediction. They're going to talk about p-value and confidence interval, things like that. It's an uncertainty measure. And cross-validation was also invented by 2 statisticians, Allen and Stone, independently. And machine learning, the first phase of machine learning, put the 2 together, really make huge progress and brought in machine learning, like optimization as well. So cross-validation, I mentioned science before. We can view cross-validation as an implication of the principle of replication from science. So we basically, if you have data, and somehow, I mean, you have to use your domain knowledge to make an argument that you can chop off this block of data into 4 kind of exchangeable bits. Why you can do that, the data collection, the context, and you basically have to argue that the dependency is not there or it's not important to take into account. And you kind of come up with 4 different prediction problems and like 4 replications of the same experiment and smaller. And then you do prediction, take the red bit out and use the blue bits to do the prediction. So it's really pseudo replication. And it's very much an application of this principle of replication in science, right? Anything a lab developed, any important discovery should be reproduced by independently by another lab. And here you try to use the same data to say that we can have 4 kind of pseudo replications. For time series, this is apparently most time a bad idea. But you can make a case, something may be stable. And therefore, for that problem, this is a good idea. And then you have to argue that. And that's a part, I think, statistics, we need to pay more attention to make these arguments, use the context knowledge, and just start using symbols. And as I said earlier, prediction cross-validation, both natural and simple. Very easy to explain a layman. Everybody understands prediction. And you say, cross-validation in some way, you try to replicate it. and also it's not hard to understand. And data availability, computing power increase, and open source software, right? So this really drove machine learning to huge success. But machine learning is coming back to something statisticians, the best statisticians always cared about, interpretation. So now that you see this reemergence of inference or interpretation. So interpretation is a lot more than just inference. Inference should serve the purpose of interpretation, and we might revise what we mean by inference. So cross-validation is usually pretty good for selecting models, avoiding overfitting. But cross-validation error often is not very good as the estimator for prediction error. So there are two things cross-validation can serve. One is select smoothing parameter. It still works pretty well. But if you use a cross-validated prediction error as an estimator for the prediction error, often it's quite off. So you better use a test error. But even when it serves well for regularization selection, say smoothing parameter, ridge regression, or lasso, for ridge, for lasso, it turns out that you have a lot of instability with the smoothing parameters selected by cross-validation. So that's actually the entry point for me to start developing or kind of unify stability as a general principle. And EU 2016 has a general, you already have a regulation saying that the users have a right to explanation. Therefore, we need machine learning and statistical algorithm to be humanly interpretable. So as a group, me and my students were working on actually a paper, precision paper, to really define what we mean by interpretation. So that's also try to combine our knowledge from different subjects. So my group have different subgroups in neuroscience, genomics, and text mining, and also causal inference. So we really try to pull our experience together from different sub-areas and do this interpretation paper. A lot of stability, and what I talk about here, is also coming from teaching the PhD level applied statistics course for the last 10. I taught 8 out of 10 years. And I find that it's really hard to get people from outside statistics to really get on top of it the way we usually teach. Just a lot of details, pretty flat organization knowledge. So that's also, 5-6 years ago, I started talking about prediction first in my teaching. I just found that that was very easy to explain, and easily they can do something with it. So make it very, very accessible. And then started developing stability as a way to bring back uncertainty, but also extend uncertainty measure to situations probabilistic models don't quite work. And also I want to have this data science platform go beyond probabilistic thinking, right? For PDE, right? Applied math is really part of data science. And PDE doesn't have to be stochastic. So how can we build a platform to also include PDE models? And one principle in terms of have the human organization is that my students are embedded in labs. So they'll work with like neuroscientists, and they will go to the group meetings. And for the genomic people, actually, they spend more time in Berkeley Lawrence lab, in a Drosophila lab. And the approach, personally, if you really care about impact of a statistical method, I find it most successful, you actually try to solve one problem and when you develop the methodology. If you have lots of methodologies, doesn't even solve one problem, I feel like the chance going to solve other problems is very small. So it's like solving one problem and then generalize. So that's the approach we take in developing these principles as well. So what I try to explain in this talk is called PCS workflow. So we start with predictability. It's kind of building on the popularity of machine learning exercise. So introduce that as a goodness of fit, reality check. You want something that at least works for prediction. Okay, but how do you know it works well? That's, I'll tell you in the particular problem how we decide on that. And the other one is computability. It's always there. And then stability. Stability is a concept. You can see it as generalization of sample-to-sample variability under a probabilistic framework. But it's also applicable when you go to pre-processing. When you go to EDA, you want whatever the pattern or the normalization method you use doesn't dictate the conclusions you draw from the data. And I'm also working on a book with my student, Rebecca Butter, and she made this beautiful drawing. My contribution is to add data as the soil in this drawing. So stability as the roots really ground us, and computability is the trunk, support all our enterprise, and we have fruits, including prediction. It could be interpretation, put it there. And I'm also working on the 3 principle paper. Actually, I just invited my student Carl to join me for that. So when I was talking about stability for a long time, I felt like it was so self-evident. I'll start asking around, right? This must have been, discussed before. And a philosopher friend of mine pointed me to Plato's, this sentence from Plato in Meno. He said that that's why knowledge is priced higher than correct opinion, and knowledge differs from correct opinion in being tied down. So knowledge is stable. Knowledge is stable, and opinion, even it's could be correct, but it doesn't have to stay the same as long-term as knowledge. So 2013, this paper appeared in the Bernoulli's special issue to celebrate Bernoulli's publication of the probability book. And it was actually a talk I gave for the Bernoulli Society's Tukey lecture. So that was 2012. And the time, actually, giving the lecture gave me the opportunity to really think things through, in the sense that I was working a lot on Lasso for neuroscience at the time, after a lot of theory, but I was really seeing how it works. And there was just so much sample-to-sample variability in high dimension. And then knowing Tukey work very, we attribute robust statistics to him. So there's also this model stability, right? So you want something under different models, things will still stay the same. Still stable. So try to put it together, start developing now called stability principle. It's also thinking it as a minimum requirement for reproducibility and interpretation. And now I'm getting into causal inference. I see predictability and stability. Computability is always there. I won't emphasize too much in this talk. It's also a way I'll call scientific recommendation system. So we know that prediction only gives you association. You identify factors. But if you add stability on top of that, it's still not causality, but I think it's a stronger evidence towards causality than just predictability. And we rely on experiments to really prove causality. So it's really like scientific recommendation system. But both projects have that purpose. So what's stability principle? You need to define yourself. What's appropriate perturbations to data or to model or to algorithms? So it's in your hands. But I would like to think this workflow will require you to write arguments to argue why these perturbations are appropriate. So this is really try to get us away from just start writing x1 through x and IID random variables. I think that can hide a lot of problems with the application of statistics in real problem, because we don't really think very carefully why is IID, because just accept it. We start. So for one of my year's class, I asked students to go back to 1930, Neyman and Pearson's paper on their testing, near Pearson-Lemma related paper. And they spent 2 pages, just language, narrative, to define the problem. You look at, and that was 2014, you look at like current biometrical paper, very often the first paragraph, you see notations. And that's a problem, because when we do that, the connection of random variable to reality is never discussed. And often it's very, very shaky. And later we take probability very, very seriously and claim significance without ever discuss why the random variable should be there in the first place. And that could be very problematic. We're kind of putting our enterprise on very shaky ground. And the data perturbation is also model perturbation or method perturbation. It's also for data preprocessing, right? For genomics, we all know that normalization method can make a huge difference to the results. So you have 2 normalization methods, and they give you different results. Is that the normalization method, or is what you discover is really scientific truth? So that step, stability, I think should be really discussed. We should really start owning the pre-processing stage of data analysis and data cleaning as well together. And it's much harder to put a probabilistic model on data cleaning. But stability can be talked about. That's why I see stability as a more general principle. And also EDA, when you look at data visualization, you might perturb your data a bit, see whether the same pattern appears. If not, then you might not want to interpret the pattern. And we'll make so many human ad hoc decisions. If you make a different decision, would you have the same result? All of this, I think we need to make it transparent and let the users of our result decide themselves. So it's really present the evidence as transparent, as honest as possible, so the downstream user decision maker can see, instead of just hide behind notations and say, oh, we know it's right. I just cannot. One thing I ask, like, if you're going to recommend doctors certain result, think about whether you want your kids to be treated by the doctor based on the recommendation. And that'll really ground you to know how serious we should be. And precision medicine has become a very big application of statistics and machine learning, and it's going to go there. Algorithms will enter decisions, and we have to take it serious, because first, for me, I don't want to be treated by algorithm that I don't trust. And the time will come. Your doctors will be looking at results from algorithms. And how serious we are, I think, is really put down all these landmarks for people to fill in. Why this perturbation is appropriate, instead of just, oh, let's just do bootstrap. Why it's a reasonable bootstrap? And also, you have to define your targets of interest. Sometimes things relatively stable for a target info. Prediction, for example, deep learning, it's pretty stable, the different versions I'll show you. And what's the stability measure? So have all these things just clearly defined and argued, I think will really help us to decide on, for other people to decide whether they trust what we do. But all of this rely on subject knowledge, experience, judgment, data collection process, resource, regulation, and interpretability. Statistics is really at the borderline of, I would say, like, very physical science and social science. We use a lot of judgment calls, and it's better to be upfront and transparent with all the decisions we make than try to hide it behind, oh, this is all objective. We all know it's not. And other people actually believe it's very, very objective when we hide behind p-values. Of course, stability principle is really try to unify vast literature on bootstrap. I would say like jackknife, that goes back much, and jackknife goes back to the 40s. And it's called algorithm stability in machine learning literature, but they do theorem in different ways. And model selection, people already started using, using bootstrap to do model selection. Clustering, people use stability, instability as a way not to go for certain clusters. Causal inference, as a young colleague of mine pointed out to me, Peng Ding, that very basic concept in causal inference is actually stability concept, like the suitable. You basically assume that the treatment to a patient, say aspirin, has only one form, right? You basically saying that the liquid form, different form doesn't make a difference. It's only the dose level matters. Right, but that's assumption, because for some people, there might be interactions. If you take a liquid form of some medicine, it will take a capsule form. Capsule might interfere with how the absorption of the medicine. So all of this, you assume that away to only allow you to look at the dose. And differential privacy is actually a form of stability too. So I want to argue that stability is very fundamental. Of course, constant doesn't matter. That's why it has to combine with predictability, that so whatever you do, capture some reality. Constant is very, very stable. I think none of us is interested in studying constant. So you really need to look at things that capture reality, and among those models, you want to look for stability. Statistics, we want small variance. That's really, you want something quite stable, right? You want less variance, less instability. But that's only one particular form of perturbation, which is sample-to-sample perturbation, which is already assuming that there's another incidence. You could observe similar data, and then you want to see the difference. That's also stability assumption underneath random variable concept. You're assuming that there's another possibility you could observe related data you can put them as realization of same random variable. Otherwise, you shouldn't care about random variable. You only care about the data in your hands. It's a little related to potential outcome. That's where I start thinking about random variable. So now when I teach that class, I don't introduce random variable until half semester. When you don't need random variables, I think for prediction, a lot of times, you don't have to go there. And one thing I always had problem with since I was a graduate student is like the postulation of a true distribution in statistics. I mean, we know it, experienced people know it, but when you teach undergraduate students use the word the true distribution, and later you tell them actually it's not true. It's just very confusing to see the list, right? We know true distribution is just a postulate, it's a construct. But when a lot of people who are not as rehearsed in statistics as we are, they think, of course, it's true. There's a circular argument. Because the way we teach, everything, of course, is true. And we never ask them or teach them and show them how to know it's not true. So all of these words can cause a lot of confusions in practice, especially statistics and machine learning is being used wider and wider. So I think we have to be careful what words we choose. And stability doesn't really require a true distribution. It's very clearly just you define a perturbation and how things change. And could be a true distribution if you think that's pretty much true. But it's just incident. It doesn't have to be the case. Central limit theorem actually is the stability result. I don't know if you guys learned central limit theorem in graduate school. I learned it through characteristic function. So it's a Fourier analysis type of proof. Terence Tao, who is a Fields medalist in the US, UCLA, has very nice notes of central limit theorem. He has 7 different proofs. And one proof is called Lindenberg swapping trick. So you prove central limit theorem by, you have ID x1 through xn, and you swap x1 by y1 with the same distribution, and you swap one by one. You can swap all of them and control the difference of the change, the perturbation change through a Taylor expansion type of argument, and you can show that you have the same limit. And then use the same swapping, you can show also this limiting distribution has to satisfy ODE, ordinary differential equation. The only solution is the normal distribution. So that's one way to prove central limit theorem. That's a lot more general for other limiting results, like a lot of random matrix results can be shown that way. It's through perturbation. So fundamentally, this limiting result in probability theory often are stability results. As I mentioned, cross-validation through pseudo-replication of experiments is one form, but you have to make the case why cross-validation makes sense. You don't want to destroy important structure by cross-validating. It's not like you have dependent data. You should never do cross-validation. But you need to argue the aspect you're looking at the data, things are not bad when you divide them up into different blocks. You're not destroying vital structures by doing that. Or you should say the vital structures you want to keep are still there within the subblocks. Bootstrap, again, we know time series, you don't want to just scramble them up, you want to do blocks. Subsampling. Leo Breiman, who was very much responsible for, for me actually get into machine learning when he was a colleague in the statistics department, he would add some noise to data, right? Things don't change. And if you really trust a linear regression form, a linear, say, autoregression model, then you can also bootstrap residuals. But again, when you argue for the appropriateness that the linear part better be pretty much right, otherwise you screw up. You have a data perturbation form could be very different from your original data. That could be problematic. I also want to include 2 other forms of data perturbation to bring in stability, right? So one thing is do data perturbation to assess instability or assess stability. You can also bring in mechanistic simulation models, say from PUDE, as a way to bring stability to some problems. For example, that's actually inspired by the robotics group at the Berkeley, Peter Abel's group. They try to teach a robotic arm to reach, say, for a bottle. And they could ask the graduate student do a lot of those reach the bottle and do video analysis, and that's the data. But they also added data simulated from control theory, basically artificial arm. And they also produce a lot of that way. And together with the video data, they really have the learning algorithm. So it's really you bring in, so it's kind of bringing, instead of, we have German-Stein shrinkage. You can shrink to 0, but 0 doesn't mean anything. If you can shrink to a better place, which is kind of captured by this PDE, then you were better at learning. I mean, in climate study, I feel like similar, right? You have all these PDE-driven models. You try to match with data. It's really a combination of mechanistic models with observed data. And together, you have the power. And there is really bringing stability. And also in deep learning, there's a lot of the adversary examples, right? People put those examples back for training to add stability. So all of this, not really under subsampling or bootstrap, but I think we can consider under the stability platform. Also model perturbation, right? For us, I'll show you, we have 18 models, give very similar prediction performance. And Bayesian modeling, people do sensitivity analysis. And for non-convex optimization problem, I think each mode actually serves a well-defined model. So you have multiple models again. There's another project, we introduced stability-driven non-negative matrix factorization to say that the number of components you choose there should bring the biggest stability. And back to my last point, I'd like to see causality as a whole spectrum instead of causal or not, right? As we know, the most famous example using observational study is smoking and lung cancer, right? It was a bunch of 20-some observational study until in the early 60s. NIH in the US had an organization, had a committee of people, human experts, who made the decision it's causal. That's why most of us believe smoking causes lung cancer, right? But some of my smoker friends don't believe it, right? So because we don't really have, like Hooke's law, in this physical science sense or physiology sense to know what exactly happens from the nicotine to lung cancer. So that's still missing, even today. But most of us believe there's a causal relationship. So there's a whole spectrum. On one hand, the holy grail is physics laws, right? You have Hooke's law. I put a load at the end of a spring. Hooke's law is going to predict pretty precisely how long the spring is going to enlarge. But there's measurement error, right? It depends on the material. If the material is ready to break, sometime I put it down, it's going to break. So the Hooke's law doesn't work at that critical point. So even there, it's not 100%, but it's very reproducible and stable. On the other hand, you have statistical causal inference, I'll call FDA causality. You care about average effect of a drug over a group of people. And now causal inference on the statistical end is moving towards heterogeneous effect, subgroups, individualized medicine. So it's kind of moving towards the stable and individual level. But still, there's a whole spectrum. So what I'm proposing here, which we have been practicing in my group, is we use prediction, we add stability, defined by the user, and then we have interpretation. First, I actually wanted to have that for interpretability, right? If things are not stable, why bother to interpret? And now I'm adding, it can also be for intervention design. So you can see the whole paradigm is still evolving, even in my group. So I want to show you two examples of practice of PCS, predictability, computability, and stability workflow. And the first one is ongoing. We're writing it up. A lot of these applied projects take 3 or 4 years in my group. And Risa is a current EE student, Yuan Si, current stat student, Adam, a former stat student, now at Google. Mike just graduated from Jack Galan's lab, and Ben was a postdoc 10 years ago, now an expert who collected the data. So now we try to put a neuroscience together with deep learning, and Jack Galan is a neuroscientist at Berkeley. He's a long-term collaborator of mine for the last 10 years. So the data come from a very difficult visual area, V4. So there are two pathways for visual information processing. One is where, one is what. So I'm looking at the what pathway from V1 to V2 and V4. V1 is the back of our head. It's edge detector. and orientation detector, and also frequency detector. So it's relatively well understood, but there's still people studying V1. That's one thing about science. We think we know, but of course there's things we don't know. And V2 it's a little more complex, but very similar to V1. And V4 is before IT. I don't know if you heard about IT. It's object recognition. People have found neurons who care about particular famous actress' face and things like that. So it's very specialized in IT. V4 is the middle. It cares about complex shapes. But when you leave simple shapes, there's almost infinite possibilities for complexity. So people have been using geometrically designed shapes to probe V4. But it's almost like you never know you miss something, right? Because when things are complex, we don't know what they mean by complex, actually. It's just not linear. So people tried, curvature seem to matter, and different shapes and all that, but you never know for sure what other shapes it cares about. You just don't know how to probe. So how to probe this V4 neuron is very much a challenge. We hope our modeling actually give you some suggestion how to probe this V4. On the other hand, there's all the rage about deep nets, right? Deep learning. Actually, people in deep learning declare that now they don't call deep learning anymore. It's called differential programming or something. They're really good with new names. They do attract a lot of young people, so I kind of feel like we need to be better at names in statistics. They do attract a lot of talents. My 14-year-old son will say, I want to do artificial intelligence. He doesn't say he wants to do statistics. He's actually trying very hard to avoid taking statistics right now. So we don't have that great a reputation. So the data was collected by Ben Wilmore 10 years ago. Nobody has really analyzed this data. It took 2 years. So there's a behaving macaque and with 71 neurons from 2 behaving macaques. And we put them together because we didn't see any difference. They're isolated visual neurons in V4, probed by these complex artificial shapes to know that it probably cares, and randomized images from a black and white image database. So the question we try to answer actually start from the second one. Really, what do V4 neurons do? So in neuroscience, in physiology, that's the tradition we took. Neurons are characterized by the stimuli that gets excited about or gets depressed about. So it's like, if you think of the response as a function, it's described by the argument, the image that give the highest response and the lowest response. So that's what we're going to follow. And then indirectly, we also lend some evidence to convolutional networks. It's a specialized deep learning with some invariance. Does it really resemble brain function? Actually, to my surprise, I think we learned some evidence for that. We started with 2-stage sparse coding and have very good state-of-art performance. So what do you mean by good prediction performance? We used V2 as a benchmark, which is an easier visual area, and whatever the best model, the prediction accuracy, we use that as a benchmark. As if V4 can achieve similar accuracy, we think we do a good job. So it's very much past experience. And it's transfer learning, I'll explain. We get the state-of-the-art prediction performance and compare with V2, and then we want to have a stable interpretation of these predictive models. So as I said, we developed 2-stage kind of deep nets ourselves, use sparse coding, which much less data, and we got pretty good prediction performance. And later we tried the deep nets to see how it works, and actually gave slightly better prediction performance. That's why we start working on deep nets. So ImageNet is this very famous now collection of images, about 14+ million images, and hand-labeled by humans, right? So people say AI will solve all our problem. I wrote a little paper with Carl again on artificial intelligence and statistics. The argument there we make is that we see the future of artificial intelligence as a human and machine collaboration. It's not just machines. Even self-driving cars, the big companies don't want to say it very much. Actually, there are a lot of human-labeled difficult scenes that the machine cannot handle. Street street change, construction change, there's events, which is a lot of things that you call domain adaptation, whatever, that machine cannot handle. So there's always human in the loop. You hope there will be less and less human in the loop for a particular task, but then human have to be involved for the next task. So it's really a collaboration future I see for AI. So this is trained for 1,000 different categories, human label data, and we take the first 2 layers, use it as a black box feature extraction, fix the weights and everything, trained on this classification task for 1,000 categories like cat, dogs, salamander, the different categories. And this pipeline start with color image, and we have black and white. So we just turn the black and white image into colored image, just make all 3 channels the same. And then we extract the features with the first 2 layers. We also did 3 and 4. We use prediction performance to compare. And 5th, you don't get as good a prediction performance. And then use very simple regression, either ridge or lasso to fit with neuron activity. Right? We have neuron activity, use spike rate of spikes over certain intervals. So this is transfer learning because we had color image to black and white. We have human data to macaque data. They are both primates, but they're not the same. And also from very high level activity like categories to neuron activities, but we did adapt for the last one. So, and it worked really amazingly well in the sense that because we had a hand-tuned model with sparse coding, and this just beats it with very much simpler methodology. But we build on top of what people have developed. So this is one example. I took 3 deep nets called AlexNet, GoogleNet, and VGG, built on the same ImageNet, and put lasso. And that's the 3 colored time series you see. They're very basically identical, right? Correlation 0.92. The dotted lines, the data. So they all have problem reach the highest. Lower, actually, they went pretty well. So it's kind of compressed. And I can take layer 3, do the same thing. Layer 4, and ridge and lasso. So we end up 18 models. Prediction performance, pretty much the same. And now we want to interpret. So we use stability to really prevent model hacking, right? We have p-hacking, but you can also have model hacking. People just try all kinds of different models. And if they don't tell you, they pick one, and you know you cannot trust it. So we think you should really seek consistent interpretations of these models. So now actually we have a new name, I should call Deep Tune. My student got really good with naming, right? Deep Dream is what people use in deep nets. So what you do is that you have this now fitted, they usually take the intermediate node, a feature, and we take the final model response. And you have this multi-dimensional surface. You start with a random starting point, and use some regularized surface, and then you just work on that regularized surface until you have gradient close to 0. So with lasso and ridge, these are the, we should call deep tune images that characterize a neuron. Remember, as I said, neurons from physiology are characterized by what signals it gets excited about. So this is saying this neuron seems to like this curvature type. But look at the lasso one, they have finer structures. We're not going to try to interpret because we think it's an artifact of lasso because we don't see it at the ridge. In the face of the evidence of they give equally pretty good prediction, we want to look for the consistent part. And, well, they're supposed to play. Yeah. So that's from a white noise starting image. You can see it works over and see the pattern appear. And down there is a graphic visualization tool comes from my group with Berkeley, we call it superheat. So this is try to do better job than parallel coordinate plots. which I can never interpret. So what you have, you use a matrix. Each row is the x vector. And on the side, you plot the y. So it's kind of high-dimensional xy plot. And you rotate the rows, and this is a progression of convergence. So that's where you see that things are pretty consistent, and you see actually here, these are all color filters. Nothing happens, which makes sense because we have black and white image. And this is something my group, other people using it, and on the top, you have summaries and things related to the X. Remember, I have 18 models. I'm only showing you 9 relate to ridge. Actually, we like the ridge model better because we think ridge is smoother, and we don't think a neuron will skip pixels to care about this, not that. So we actually use biological knowledge. We like the ridge better. You can see that they all have this curvature, but there's a lot of variation of details. We now actually has a way to put them together to have a more, like a single deep tune image. That hasn't entered my, just last week, hasn't entered my slides yet. And you can see layer 3 with GoogleNet, the curvature is pretty faint, right? And you have all these eye-like things with GoogleNet. It seems to be only for GoogleNets. So we don't want to interpret. We only look for the high-level curvature. And there's another project with RISA. We can also remove a lot of the nodes. We can remove up to 80% or 70%. You still see the same pattern. So that's another stability, showing that the pattern is kind of there, which I should call the deep tune. And we also look at, remember I only had a black and white image. I look at the images in the database, not any possible images, and look at which one excite the neuron. Again, you see that there's a curvature signature. So we try to look for many different evidence. 5? So that's one project. I'll say the second project very quickly. So this is 10 of them. You see the diversity. So this characterizes the different neurons. The second project, I only have very little time, but I want to mention it. It's put stability on top of random forest. With Samantha, who is now a professor postdoc in my group, and with Ben's group, Ben Brown, and Carl is a student. Samantha now assistant professor at Cornell. So it's about genomics, and we try to figure out function, like high-level interactions between the different biomolecules to understand certain functionality of them. So transcription factors are very important biomolecules. It really controls on and off switches for gene expression. And we take advantage of this French flag model, saying that for development stage of Drosophila, fruit fly, there's this phenomenon and thresholding phenomenon. So that's how they decide what happens and where. So that's why it's a good match for this mathematical form of rules or decisions. So you need to have enough biomolecules for things to happen. And that's a thresholding behavior, which came from biology. And we really want to give interpretation. And random forest, you guys probably have heard. I won't say much. And the iterative random forest just appeared in PNS. It took us 3+ years and was also building on Ben Brown, my collaborator, co-lead of the project, 10 years of experience working with random forest. He really liked random forest, but he knew it was not stable for interpretation. So iterative random forest, high level, we stabilize random decision trees by do many different runs and look at the stable bits. And we interpret it, and then we have an after loop of bagging to assess interaction stability. Okay, so it's adding stability in different ways. We use Gini index, and we do reweighting of the features, depends on the Gini index scores. And we build on Shao and Manhausen's random intersection trees, which is binary. So we turn a path in a decision tree into binary, saying that if x1 gets split, it gets a 1. If xy gets split, it gets a 1. The rest doesn't get split down, gets 0. So we turn our problem, random forest, into a 0-1 intersection tree problem, which had a very good, again, randomized algorithm by Shar and Manhausen. And that's the ingredients. And we end up with a stability score. We back the whole process again. So many layers of randomized algorithms. So for Drosophila enhancer predictive prediction, we have 80 chip assays, binding, histomodel, just predictors. And we have sample size about 8,000 different sequence. We want to predict the enhancer status. It's a classification problem. This is, we work with the Drosophila lab, so we can find on your right-hand side, you see the name. The blue ones are the three-way interactions. The letters are the different names of genes. Red ones are pairwise. And on the other hand, you have the scores are the stability scores. So you look at over 50%. And to our nice surprise, 80% of the two-way interactions we could find with help of Sue Seneca, who is the lab we work with, that people already had done experiment to show the physical interactions in the literature. So this was a very nice surprise that the two-way interactions, we find over 0.5 stability score, 80% of them already written in the literature. They were real interactions. For three-way interaction, the technology is beginning to appear to actually do the experiments. For the three-way interaction or higher, our results serve as our recommendation system. So far, it will save biologists some effort to find real interactions. So that's the interaction part. But we use a two-way interaction as validation. So this is, you can see, this is one surface we plotted from our result, that the three genes, when Krupo is low, you don't see any interaction between Zelda and Giant. These are the names of genes. But when the Krupo level is high, you see interaction. So this is a three-way interaction. So the signature pretty clear. There's also a theoretical bit. We're working on paper connecting stability, generalization, and risk of convergence as a step, surrogate for computability. Okay, to finish, the PCI workflow really is that we want to use stability to go beyond just sample-to-sample variability. And when you have predictability as a reality check can work really well together. And I've shown you two cases that you can use it as interpretation and scientific recommendation. For the first example, with all the deep tune images, we can, if the electrode is still in place, you can feed it back, use the neuron to prove that the neuron is excited about this image. It really solved the problem of finding stimuli. Remember I said the complex shapes are very hard to find, right, if you just do geometric complex shape. This have also generation of stimuli. I also want to mention that you need to work on structure match of model and domain knowledge. For the first one, I don't think deep learning will work as well for the second example, but we're trying to see. Maybe I'm wrong. But the first one, for visual, for that problem, if you use random forest, I think the structure is not, even both are very good nonlinear methods, they're still a little different. Even when we have big data, we don't have enough. So let me just mention, thanks to my group, and this Berkeley Data Science Initiative. So our reports on the internet, we're looking at a new division, some sort of data science. And CS and staff faculty have been working to co-creating and co-teaching 2 courses, now serving about 3,000 students a year. I was on the team to have done Data Science 100. So the idea is that you learn Python programming with a Jupyter notebook. If you haven't heard it, check it out, IPython notebook. And when you learn statistics. So you don't separate programming with statistics. You do it together, and the first level is DS 100. Now 1 semester, 1,000 students, and DS 100 now 3rd semester. I was on the team for the first run. Now I serve 600 students a year. So I'm also speaking as a parent. My daughter was in the class, now in the 2nd class, and really having a good time. And check out Jupyter Notebook. It's really a useful way of doing both the narrative and also the data analysis. Thank you.